So the next thing I want to do is actually walk through the entire MIPS instruction set here um, on the sheet and walk through every kind of instruction that we have so that you have an idea of exactly what's available and what maybe not available. Don't forget, there are three basic kinds of instructions in an assembly language, and in MIPS particularly. They are data manipulation instructions. We call these ALU instructions because they use the ALU to change information, take two registers and manipulate them in some way and change the content of a third register. We also have a branch and jump instructions, which are called program control flow instructions. These allow us to, instead of just executing the next instruction in the list, allow us to execute a different instruction, either based on some condition for a branch, like if you're going to do an if statement or a while statement or something like that, or unconditionally with a jump, if you want to just move to another place in memory and start executing code there. This would be like for a subroutine call. And we'll see applications of all of these as we go. And then the third kind is load and store instructions, which allow us to move information from memory back and forth into a register. This is basically all we have. So I want to walk through every single one so you really understand how these things work. We've talked about a number of these already, so some of this should be clear. We have the arithmetic instructions. This is the first 6 that are on our list here. Add, add immediate, add unsigned immediate, add unsigned, subtract, and unsigned subtract. And these do what they say, right? We add two registers to their values and put them together and put the result into a third register. That's add. And we can do that in an unsigned way. And that just changes the way that we interpret the flags. But it's important for the ALU to know whether the add that you're doing is signed or unsigned, so it can know whether or not the result is reasonable or not. And then we have immediate versions of these, where one of the operands is the 16-bit immediate value that is the bottom half of the instruction. So we'll walk through an example of each of these. Add, for example, if you look at the way that add is encoded, it's an R format instruction, and it uses ALUR category. Now, the way that the sheet is set up, again, if you look way down at the bottom, you can see that the R-type instruction has an opcode first, and then RS, RT, and RD. This is S and T are the two sources, and D is the destination. The shift amount is not used in regular ALU instructions, but we'll talk about those in a minute. And then the function code tells you actually what instruction we're doing. Opcode tells you that we're doing an ALU R-type instruction in this case, because those are all 0, 0, 0, 0, 0. There's a bunch of them. And then the function code specifies that further to say what kind of ALU R-type instruction we're doing. Then we look at ALU R category, and over here we have a bunch of information about each of these categories, right? It says that add into RD goes RS plus RT. So it tells you what's actually happening, and it tells you what the assembly code looks like, and then gives you some notes about how anything else that might be interesting or important. For example, for R-type ALU instructions, the opcode is extended by the function code, which is what we just said, right? The function code tells you, so the opcode for ALU R-type instructions is all zeros. The function code then tells you you're adding or adding unsigned or subtracting or whatever. So then we have immediate versions of these instructions as well, where the format here has RS and RT. In this case, RT is the destination, and RS is one source, and the immediate value here, sign extended, is the other source. And don't forget, you can always look at your data path to sort of remind you of how these things are working. One thing to notice is that there is not a unsigned subtract. There's not an immediate subtract. There's an unsigned subtract, but not an immediate subtract. Why would that be? Well, that's because you don't need an immediate subtract. You can do an immediate add with a negative immediate value. So this is an efficiency that the designers of MIPS have chosen to implement fewer instructions, knowing that the functionality of those instructions can be got by other instructions. This makes it particularly difficult to write code sometimes because you might think that there's an instruction available, but it isn't, right? You might want to do an immediate subtract, but it doesn't exist. It's not in the instruction set and you can't use it. So what you have to do is change that instruction into an immediate add with a negative immediate value, and that might make your code a bit harder to read, and it might make it a bit harder to write. But this is one of the trade-offs of what we call reduced instruction set computers, or RISC computers. is that they are not optimized necessarily for making it easy to write code. They're optimized for making it efficient to operate. One way to make it efficient to operate is to have fewer instructions, because that means we have fewer opcodes, fewer function codes. We can fit more instructions of more complexity into the assembly language itself, and there's fewer things for the machine itself to do, which means it can do them faster. So keep in mind that there are some things missing, and one of the things I might ask you on an exam is, why are these things missing, and how would you do subtract immediate if you don't have access to that instruction because it's not in the assembly language? Okay, then we have our logic functions. This is the next one on the list. Bitwise, and immediate, nor, or immediate, exclusive or immediate. And again, we have the opportunity to use regular register format for noring together two registers, and we can use an immediate format for oring together a register and an immediate value. And we've already used or immediate in one of those contexts to implement a pseudo instruction. The load address pseudo instruction loads the upper half of the address first using load upper immediate, and then ORs it with the bottom half of the 32-bit number, creating a complete 32-bit number. So that's one of the applications. So the functionality of these, we'll look at some examples later on, is to do things like masking, to change out some chunk of value. Maybe want to change all the lowercase letters, ASCII letters, into uppercase. One of these logical functions would be able to do that for us as well. Third on the list, we have shift instructions. These instructions allow us to take a 32-bit number and move it one direction or another. This is what that shift amount field is for in R-type instructions. Shift instructions are done a little differently. It's a very interesting setup. They're all R-type instructions, so they all use the R-type format, RS, RT, and RD, and the shift amount is what we're going to use to decide how far to shift. If we look at the category, or the sort of extra information about each instruction, you'll see that there are actually two kinds of shifts. R-type shifts and V-type shifts. If you look at the way that these are written out, the shift R-type does a shift of a particular kind into RD, the value that's in RT, shifted by the shift amount. That's what that little double left-hand sign is. So this is shift left logical. This is into register D. What's in register T shifted by the shift amount. But you can also do a variable shift. And this allows us to shift by into register D, what's in register T, shifted by some amount that's in register S. So you can either put the shift amount, which is how many bits to shift it, in the shift amount field in the instruction, or in register RS. And this allows you to hard code a shift amount or produce it into a register somewhere if you don't know how much you want to shift yet. And you can use shifts for a lot of different things, but the interesting thing here is that the most you can shift is 32, because it's a 32-bit number, and if you shift more than 32, then you are out of bits. And so the shift amount is only 5 bits, because that gives you a number between 0 and 31, and that's fine. But the shift amount register, if you choose to use a variable shift, will ignore any number above 31. I said 32 before. It's 31. You can shift from 0 to 31. And they'll ignore any number above 31 because that doesn't make any sense for a shift of a 32-bit number. And so this number, if you put the number 387 in here, it'll cut off everything except the last 5 bits and use the last 5 bits to determine the shift amount. So keep that in mind when you're doing your shift. We'll talk about these in a little bit of detail later on and give you some examples, but this allows you to shift a value that's in a register by some direction, either left or right. And there's another kind of a shift called an arithmetic shift, which we haven't really talked about. Basically, it just means that you're preserving the sign bit. So if you want to shift a number, if you want to, say, divide a number, a signed number by 2, you can shift it to the right, and that'll preserve the sign bit, and then it's called an arithmetic shift instead of a logical shift. So there's logical shifts in the left and right direction. There's only arithmetic shifts in the right direction. This is another sort of specification, another simplification of this machine, and this is fairly common for instruction sets. assembly languages is to not have a shift left arithmetic. You only have a shift right arithmetic. And we can talk about in later details, and you can look it up online, why you might think that would be. And so you can have logical shifts in the left and right direction, an arithmetic shift, and you can have logical shifts by a variable amount in the left and right direction and an arithmetic shift. And one of the things, another feature that we'll use is rotations, which allow us to shift the bits and then move them around as we go. But those are not actually implemented as instructions. Those are implemented in pseudo instructions. If you look at the other side of the sheet here, you can see rotations. And we'll talk about those in a bit of detail later on. So shifts. And then we have set. Now set instructions are useful for comparing two numbers. This is often used in concert with a branch instruction. When you want to branch if two numbers are equal, that's a nice thing to be able to compare, because you just take the two numbers and say, are they equal or not? And you can branch if they're equal or if they're not equal. But sometimes you'll have to compare two numbers for equality, if one is less than or one is greater than. And so you can do this in two phases. You can either you can compare two numbers together. You can take two registers, A and B, and you can compare them by subtracting them, but not actually storing the result. Instead, what you're storing is the number 0 or the number 1, depending on if the one was less than the other. And so here we have, as an example, set less than. It's an R-type instruction, and we can look at this R-type set instructions here into RD, RS, and RT. And what this does is it subtracts RS from RT, or it compares them for whether RS is less than RT, using a subtraction and checking the flags. So it compares RS and RT. If RS is less than RT, then it sets RD to 1. So it doesn't set the difference, it sets the value 1. And if RS is bigger than or equal to RT, it sets the value 0. So RD will become 1 or 0 depending on the comparison of RS and RT, and then you can branch on whether the values are 1 or 0. Right? Branch if equal says, looks at the register that you set in the set instruction. So say you used a set instruction to set register T0, and then you would compare it with 0. And you said if T0 is equal to 0, that means the set instruction failed, and we can branch. Maybe we want to branch if the set instruction succeeded. There's lots of different ways to do these branches and jumps, and we'll look at them all in detail. But that's what the set instructions are for. And again, there are 4 different variants. There's the regular set instruction, there's an immediate set instruction, there's an unsigned immediate set instruction, and there's an unsigned instruction. And these are R-type and I-type based on whether they are register format or immediate format. Then we have the program control functions. These instructions are branch if equal, branch if not equal, and jump. And we will talk about how these 4 different jumps work. Basically, the jump instruction uses pseudo-direct addressing. It's a J format. We look down here, we talk about the J format. And again, we'll look at this in detail, but it takes these, so it has to have an opcode. Every instruction has an opcode. That's 6 bits. It takes the remaining 26 bits and uses them to generate an almost entirely new jump address, or a program counter value. It's not a full 32 bits, but it's close. And we'll talk about why this is useful. But then if you can't reach the target that you want in that pseudo-direct addressing format, then you can use a jump register, where you can create an address in a register using the load address pseudo instruction, which then translates to load upper immediate or immediate, and then it will just put that new address into the program counter. The other 2 here we have are jump and link, and this is going to be useful for when we call a subroutine later on. Basically, all it does is it stores the value of the program counter into the return address, so we can get back where we came from. And again, we'll talk about those in detail as we go. The branches are I-type instructions. Branch if equal, branch if not equal. It compares the 2 registers, and we'll take the branch if the condition is met, and we'll just choose to execute the next instruction if the conditions are not met. They're both I-format instructions, and the program counter is changed by the value that's in the immediate field if the branch condition is met. And again, this is just a quick summary. All of these will be looked at in detail later on. Then we have our load instructions. And again, we have basically two variants, load and store. Load allows us to take a value from memory and bring it into a register. Store allows us to take a value that's in a register and put it back into memory. The load instructions, there's a bunch of examples, a bunch of different kinds, based on how much information we're loading. Load byte unsigned, load half word, which is 2 bytes, half word unsigned, load upper immediate, which takes an immediate value and puts it into the upper half of a register. Not really a load instruction, because we're not bringing information in from memory, we're bringing it from the instruction itself, but it's in the load category here. And then load word, and most of the time we're just going to use load word. Most of the time we'll bring in information in 32-bit chunks, and it'll be fine. And then we can store byte, store half word, and store word. So those are all I format instructions because the ALU is used to create the address. And again, if we look at the load instructions here, we can see how. Load word into our target register RT, the value that's in the address specified by RS plus some immediate value. And so you take the immediate value, you sign extend it, you add it to the address that's in RS, and you use that to look up some value in memory. And for load, we then bring that into the register that's in RT. Okay. Finally, we also have a few extra instructions here. Multiply and divide. We're going to talk about these in a bit more detail later on as well. But it's enough to know that multiply and divide exist in MIPS, but they're done a little differently. They're not R-type instructions per se. They say they're R-type instructions, but the result does not go into a destination register. If you look at multiply and divide, multiply only specifies 2 registers, RS and RT. Divide only specifies 2 registers, RS and RT. Because if you think about it, when you multiply 2 numbers together, the result that you get could be bigger than your sources. Right? If you multiply 10 times 10, you get 100. And the result is bigger than, in terms of the size of the result, the number of bits in the result can be up to twice as big as the numbers that you are starting with. And so you can't just put the result into a regular 32-bit register. You need the possibility of at least 64 bits for a multiply operation. Same with divide. When you divide 2 numbers together in an integer way, you're left with a quotient and a remainder, both of which can be 32 bits. So the way MIPS handles this is it says, I'm going to create 2 special new registers, calling them high and low, and they are going to contain the results of any multiplication and division operation. This happens in a completely different way. It's not actually shown on here. It's a little weird, but it happens in two passes. So first of all, say for example, you're going to do a divide. You give it 2 registers, RS and RT, and what you'd find is that the quotient is stored in the special register called low, and then the remainder is stored in the special register called high. What do we do with these registers? Well, we have 2 additional instructions, move from low and move from high, that allows you to put those values from low and from high into some destination register. And so this is how we actually calculate multiplication. So if you want to do a multiplication or division, for a division, if you wanted to do the remainder of a division, say you want to do mod, first you would do divide, and you would specify 2 registers, and then you would do move from high, and that would give you into the final destination register the remainder of the value they're looking at. So it's a little bit complicated, and again, we'll give you some direct examples. And there is a pseudo instruction that is a 3-register multiply that just ignores the high register. And that's usually okay, right? Because usually you're not dividing numbers that are in the 4 billions. You're not multiplying numbers that are in the 4 billion. So most of the time, the upper register, the high register, is empty, and so it's fine. So those pseudo instructions exist. So that's the full list of instructions that you need to know. There are a few extras that might be useful. For example, there are branches comparing to 0, which are a little bit more complicated. They use 2 registers, and then they specify the branch type in a 3rd code. The branch code is stored in the RT field, so we only get RS and RD. The RT field for these things is used for a branch code, which again gets a bit more complicated, but these are available. Then there's floating point numbers, which we will look at later on. And that's it. Those are the instructions that are available in the MIPS assembly language. And I hope that that gives you an idea of everything that you can and can't do. And again, for some of the details of some of these things, we'll revisit them later in the course, but you can sort of look ahead if you want to know exactly how shifts work or how multiply and divide work.